Okay, I think I'm recording now. So again, are you able to see everything? Are you able to see anything, everything?
Yeah, it seems so.
Okay, okay, good. Yeah, sorry about that. It seems that we have some technical issues. Hopefully, well, we are going to, yes, I think it works. It's recording now, so hopefully it can record for as long as we want. I haven't tried to record any long video on WebEx, so I'm not pretty sure whether it works or not. Hopefully it should work. If it doesn't work on the cloud, then I can try to make it somewhere like in my local disk. Maybe that will work. But anyway, yeah. So sorry about that. Sorry again. Well, maybe we should continue. And we have this n dot this vector, right? This vector is, well, then you use this inner product of these two vectors. You got n1 vux and n plus n2 vuy plus n3 vuz. Okay, so that is what you want. You have v everywhere. So it's v times n1 ux plus n2 uy plus n3 uz, right? So that's why we have this term here. It's v.
Wait, can you remind the definition of partial NU?
Yeah, of course. Partial nu is actually equals to n dot gradient u, which is you take derivative along vector n, direction n. Okay.
Okay.
So you have this, so which is why you have this first Greene identity. Let me double check. So who you are, well, it seems.
I think she is still talking.
What? Is still working on it?
She just told me that she
What? I'm sorry, I didn't hear you.
is installing it.
Okay, maybe we should wait for her, yeah. Well, sorry about that. It seems that sometimes this Zoom doesn't work well for some reason. I don't know. Yeah. So Zoom still works well for you, right? Then that's really weird because I don't think I have any issue here. So yeah, I think so. I think it should work. It also works for me. Well, I think. Oh, why is that? Yeah, I really don't know. Well, for tomorrow, we will have from from 3 to 5:30 is our class, and from 5:30 to 7 is our office hour. Okay, I just moved the morning office hour to the after class office hour. Okay, sorry about that. I have some issue to deal with. How could I? We now have 5 people, right? 1, 2, 3, 4, 5. I think we have 5 people here. Is that all? Okay. So Hu Yue, are you there? Are you there or? Okay, great. I see you. So can you hear me?
Yes.
Okay, great. So basically, you can see that, well, by definition of this, well, direction derivative along this direction n, partial n u is equals to n dot gradient of u. Okay, and what is n dot v times gradient of u? Is just equals to v times n1 ux, n2 uy, n3 uz. So it is exactly n dot gradient u times v. Okay, which is why we should have this term here. Okay, any question about this Green's first formula or Green's first identity?
Sorry. So like V is a scalar.
V what?
V
is
is
a scalar. Yeah, u, yes, both u and v are scalar. They are just from R3 to R1. They are real value functions, which are the function we are interested as solution to our differential equation. Okay. Then the next thing is how we will this kind of formula, it looks very complicated, and it seems that well it may not be useful for us. Why we are interested in it? Well, as a first example of application of the Green's first formula or Green's first identity is, well, for instance, we can choose v equals to 1. Okay, v is just a constant function, constantly equals to 1. In this situation, let's see what happens in our formula. Okay, then on this side, it will be partial d. You take the integral of partial n u. On the boundary, you take the surface integral. This part, the second term, well, the first term on the right-hand side is actually 0, right? Because the gradient v equals to 0. Derivative is 0. So the only thing left is the third term, or the second term on the right-hand side, which is the integral of Laplace u. Okay? So which means, well, if you have a function, then you have a function u, then the function must satisfy this consistent condition. Okay? So which means if you have this, well, this boundary value problem for Laplace equation, say Laplace u equals to, I'm sorry, equals to fx in G, and partial where you have this Riemann boundary condition is equals to hx, or, well, on the boundary. If you have this boundary value problem and you want to solve it, okay, in order to get a solution, we must have the consistent condition for it. That is, you take the boundary integral of fhx, it must equal to the total integral of fx. Okay, this is the consistent condition that we must have. Is that clear? So we must have this condition based on the Green's first formula, Green's first identity. And it turns out that this is also the almost sufficient condition to guarantee the existence of the solution. Okay. This is something we are not going to prove rigorously. Okay. And almost sufficient, that means, okay, we must have some smoothness of F, smoothness of H, and smoothness of the boundary of D. Then in that situation, in this kind of constraint, as long as you have these two quantities are equal to each other, then you have the existence of the solution. Okay. Any question about it?
Yeah, actually, so wait, so
Mhm.
that the green theorem works for like any specific functions because we didn't use much properties there. Um, and so like, oh, why does the fact that green theorem holds for something show that there will be a solution? Because it feels like it holds in most of the cases.
Well, it holds for anything. Okay. This Green's identity, Green's first identity, it works for anything. Okay. It's just like, well, it's just like something like integration by parts. Okay, in some sense, it's just like an integration by parts formula. Nothing more than that. So which means it's just a tool. It cannot really help us to guarantee some existence of the solution or something more than that. It's just a tool to help us to check whether we can get some existence or uniqueness of the solution or not. Okay, you can treat it as the integration by parts, not really like something highly relevant to PDE. It is relevant to us simply because, well, we have, well, this Laplacian here, we have the boundary terms here, so that sometimes if we want to do some analysis of the solution, then we can use it. But in particular, well, we don't really know when should we use it. Okay, so sometimes we have to by try and error to check something is true or not. Okay, it's just
Um,
like intuition method. Mhm.
but like, okay, so my question is, so what is a sufficient condition to have existence almost of the existence of the solution?
This is a really good question. Yeah, this is a really good question. So it seems that we just get it from nowhere. Maybe I also have some kind of echo. Uh, well, so how about now? Do you hear any echo, or can you hear me clearly?
Yeah, fine.
It's fine. Huye, so how about you? Do you see? I can hear some echo from Ayas. Yeah, I also feel that like that. Yes, when Aya say that, well, I can hear something from Aya. So is that okay for me? I mean, when I say something, is that okay for me? Okay. Anyway, so uh, it's okay. Well, maybe if you really if that is really Aya's issue, then maybe Aya can just send us your questions via WeChat, so that it's easier for us. But anyway, yes. Well, that's a very good question, which is how you can guarantee the solution exists or not. Well, this is only one equation, and you check, okay, it's satisfied, then you guess the solution exists. It seems like a miracle, right? It's just from nowhere. So this is really hard. This well, the consistent of the equation of the PDE is a hard problem, I have to say. And in order to get a better understanding of this kind of problems, you can just try to imagine. For instance, you have a boundary condition here for your differential equation. It must be satisfied. Okay. Meanwhile, you also have this Laplacian of u equals to fx everywhere. Okay. So which means this basically tells you the second derivative of your u is equals to something everywhere. And your u has to satisfy some boundary condition for your first derivative. Okay. So in this kind of situation, then you may guess that your first your boundary condition and your this kind of inhomogeneous condition or the source term, they must have some consistent condition. Okay. Otherwise, you cannot guarantee that its second derivative is some function, some given function. Meanwhile, it also satisfies your boundary condition. Okay. But in general, this would be hard. In general, you have to well, if for a particular problem, you have to check it well in particular. Okay. So here, I'll just tell you from this course, I'll just tell you how you can check the consistency. This is the only thing I'm going to tell you for the Laplace equation. Okay. And actually only for this problem, only for this Neumann boundary conditions problem. Okay. So again, PDE is a very hard area, and you may find that in the future, if you are interested in PDE, then each of the PDE is well, is something you can learn. You can spend your whole life on it. Exactly. Yeah, you're right. We know it must be true. Well, because if it is not true, then well, the contradiction appears immediately. But of course, to know it's a sufficient condition, well, it's another story. Okay. So again, the sufficient condition to whether you have a solution or not for a boundary value problem is well, it's always very hard. And in most of the case, you have to understand the PDE in the physical sense, which is okay. Suppose you have some physical scenario or physical phenomenon, and you build a PDE, and then you try to give it some initial condition, boundary condition. Is that overfit or not from physical point of view? As long as you can answer that, then you may try to prove some mass theory. But in general, there is no general answer. Okay. And another example is, well, we can actually try to show by using the Greene's first formula, we can show that, well, for the, because we are interested in the Laplace equation, and we are interested in the Laplace equation with Dirichlet or Neumann boundary condition. And this first, well, this Greene's first identity can also tell you the uniqueness of Dirichlet problem. Okay, this is somehow like similar to the MG method. Well, suppose you have two solutions, whether you have this 0 or f here on the right hand side doesn't matter, and you have u on the boundary is equals to something, let's say some h. You have this Dirichlet problems or this well, Laplace equation with Dirichlet boundary condition. You want to see whether you have the uniqueness of the solution or not. Okay, So which means, is that possible for you to find U1 and U2 such that they both solve this boundary value problem? Then you can also use the Green's first identity. Okay, which is you can try to plug in U equals to U1 minus U2 and say V equals to U again. Okay, then what happens? What happens is this term, the last term on the right-hand side of the Green's first identity, disappear immediately, right? Because Laplace U equals to 0. Meanwhile, you have that U1 minus U2. So it also satisfies the 0 boundary condition. So which means you will have the Green's first identity will becomes partial D, and you have this V, which is U, partial N U ds is equals to gradient of U squared dx. Right? Because we take U equals to V equals to the difference of two solutions to your initial value problem or to your boundary value problem, right? So you got this identity, but you know that U on the boundary is equals to 0. So this term disappears. Okay, so what we get is gradient of U squared equals to 0. That means gradient of U equals to 0 constantly. So that means U equals to a constant on D. Okay, but we also know that U on the boundary is equals to 0. So that means this constant must equals to 0. Any question, Aya? Why of what? Oh, you see, this U on the boundary of your domain must equals to 0, right? U equals to U1 minus U2. So it is on the boundary of D. On the boundary of D, since U1 and U2, they both solve this. Well, discrete problems. So they have the same initial boundary value. So subtraction will be 0. Okay. So for any point on the boundary of D, the U must equals to 0. Okay. So everything will be 0 on the right hand side, on the left hand side. Okay. So we must get this constant must equals to 0. So which means U is constantly equals to 0. So we have the uniqueness of our solution. And another remark is, well, by the way, this is actually similar, very similar to our energy method. If you still remember our energy method. Okay. And another remark is, well, if we change this Dirichlet boundary problem to Neumann boundary problem, then by the same method, you can still see that the right-hand side equals to 0, right? You have partial NU is also equals to 0. So that means you still get U must equals to a constant on D, any point of D, right? But here you cannot really see whether this U is a constant or not. So that means, that means if you have two solutions, are both solution to this star, or maybe let's call it N, then we must have U1 minus U2 is equals to a constant. Not exactly 0, but well, you can add any constant to it. This also makes sense, right? if you have one solution to this Newman boundary condition, you add some constant, it's still a solution to this Newman boundary condition, Newman boundary problem, right? So you don't have the classical uniqueness, but you have this, some kind of modification of uniqueness of your problem. Okay? Any question? Any question? And another application, which is also very interesting application, is so-called the Dirichlet principle. Okay, the Dirichlet principle is it's actually a principle I think maybe some of you have learned from your high school physics, which is if you have some kind of object, then or some kind of phenomenon, then physically it will try to go to those status such that the energy has the lowest, right? That you have the lowest energy. This is Dirichlet's principle, and we can actually prove this kind of thing mathematically. Okay, as long as you can understand our mathematical notation has some physical meaning. Okay, so for instance, omega is a function that satisfies our some kind of physical intuition, and it satisfies the harmonic. It's actually a harmonic. It's actually a harmonic function. Okay, then what we can do is we can define the energy of our function w. Okay, for any function, it can be defined as a half of this integral gradient of omega squared, the gradient of w squared. Yeah. Hello, hello. Can you hear? Can you hear me? Everything okay? Hello. Who is A? Well, I think he or she may have some problems. Well, anyway, so if nobody else feel like any troubles, then hopefully we can watch it after class by video. Okay. So is that okay for everybody? Can you hear me? Still can hear me, right? Well, I don't know what happened, but something happened. Anyway, okay. So if you have the status of something, of some object, then if we denote it as W, then this can be seen as the energy of W. It can be, for instance, this W can be seen as the velocity. I mean the displacement, and the gradient should be the velocity in some sense. And this kind of thing can be seen as the kinetic energy of an object. Okay, and it has some other meanings, but you can just imagine mathematically we define a function's energy in this way, at least some kind of kinetic energy in this way. Okay, and I'm sorry, and let's say u be the unique harmonic function in D. Okay, satisfy u on the boundary of D is equals to h hat. Okay, let's say this is star, and then let's say let W be any other function, maybe U, maybe some other function. In G, satisfy the boundary condition as well. Then what we have is the energy of W is always greater or equal than the energy of U, which means the harmonic function or the harmonic state is a ground state in physics, or the preferred physical stationary state. Ground state or preferred physical stationary state in physics. Harmonic means Laplace U equals to 0. Okay. This is a definition of harmonic. Which means if you define this as your energy for a function, then you want to minimize a function with constraint, with restriction on the boundary, it must be equals to h. Then if you want to do this minimization problem, the result you should get is the harmonic function. Okay, this is also a very interesting problem in optimization, and meanwhile, it is also a very interesting problem, or the first problem, or maybe the most basic problem in so-called the calculation of the calculus of Barish. Okay, so let me prove it. And well, the proof is actually say first I want to say that if U is harmonic, then it's always the lowest energy. Okay, and actually what we can say is even more. If you get another function which has the lowest energy, then this function must be harmonic. Okay, this is moreover. If you have a function, if v such that v satisfies star, and will for any w satisfy star, we have this E of W is greater or equal than E of V. We must have V equals to U. Okay, so it's actually an if and only if. If you want to find the minimization of your energy functional, the so-called energy functional on the domain D, then it must be the harmonic function. Okay, so let me prove it. First, let me prove that this harmonic function energy is less than any other function's energy. The proof is very simple. Which, well, let's try to write it by, let's say, well, you have any W, you have a U harmonic, and satisfy star. Then if we set V to be U minus W for any W. Okay, that's trying to compute what is the energy of W. Well, the energy of W is very easy now. It becomes 1/2 of U minus V. We take the gradient square dx. Okay, so this is you can use well, Yes. Harmonic function is just for those functions which are, yes, which are satisfy Laplace of this function equals to 0. Exactly. Okay. So you have this, you write W in terms of U and V. And of course, you can try to write it by expand this, this square, right? So you try to expand this square, what you will get is, okay, nothing more, is this square plus the gradient of u squared plus the gradient of v squared plus the intersection term, right? So it's this gradient u squared plus 1/2 this gradient of v squared, okay, plus, or actually minus, you don't have 1/2 here, you have the integral everything, gradient u times gradient v. Yes. Okay. So this is clear, right? This is just the quadratic formula. And you can see that, okay, now this is EU, this is EV. But you have some other term here which looks very ugly. But it's not so ugly because if you still remember, we have the corresponding terms, our Green's first identity. We have it here, right? And if we plug into this, this more or less like integration by part or the Green's first identity, what you will have is, okay, it's equals to this, well, it's equals to this term minus this term, okay? So what's that? EU plus EV, well, it's minus, so let's say it's plus v Laplace u dx minus on the boundary, and you have v will u dx, right? Okay, this is awesome because if u is harmonic, we must have this term disappear, right? Laplace u equals to 0 indeed. This term also disappear, right? Because on the boundary, you must have u and w both satisfy star. They have the same boundary value. So v must have 0 boundary value. So these two terms, they disappear. So which means these two guys, if you take multiplication and take the integral, gradient u times gradient v, you take the integral, it's actually disappear. So it's equals to EU plus E. Of course, it's greater or equal than E. Okay. Any question? Any question? Okay, sure. Let me give you a second to wait for everything delay. So we will have this EW is greater or equal than EU. So is that okay now? So everybody can see This one? Hmm?
So basically, it's a divergence theorem, right? And
Exactly.
just say that those two integrals are equals to 0.
Yes.
Okay, and then we get that EV should be bigger than 0 anyway, so we get the inequality.
Yes, that's right, because all the energy are square things, so they must be non-negative, right?
Oh, okay, that makes sense.
This is the definition. Yeah. So that also gives us, well, when does this inequality becomes the equality? This will happen only if the V's energy is equals to 0, and you can also get that, okay? Then that means if you take this lowest energy, it must guarantee that W must equals to U, okay? Because on this domain and on this boundary value, you must have a unique harmonic function, as we have shown before, the uniqueness of our solution. Okay, but I would like to use another proof to show that if you have the lowest energy, you must have this function is actually a harmonic function. Okay, this another proof is different from what we have here, but it's very interesting and is very useful in terms of calculus of variation. This is actually one area of analysis, which is calculus of variation is one area of analysis, which is something like you try to take some minimization problems or optimization problems for some forms like this. And then you want to find, okay, for what kind of function it must satisfy. Instead of this minimization problems, what kind of, for instance, PDE problem it has to satisfy. Okay. So the idea of this calculus of variation is, okay, now we want to show that suppose V is the lowest energy. Suppose V or U is a minimizer. Okay. Of E. Okay. Of this energy. That's called equation E. Okay. Suppose U is a minimizer of E with restriction star. Okay, then this becomes so-called the optimization problem. Then we want to find what kind of condition that U must satisfy. Okay, then that means for any V, okay, you try to take a perturbation of V along this V direction, which means V is a function satisfy, okay, V on the boundary of D equals to 0. So that if you add U by V, then it doesn't destroy this star constraint. Okay, then let's consider U plus some small number plus times V. Okay, so which is like you try to go a little bit, you try to take a little bit of fluctuation of U. And since this U is the lowest point, so if you take a little bit of perturbation, then it must have a higher level of your function, which means it must have a higher energy.
Hey, I'm really, really sorry. My connection was bad again. So I see that you wrote something about minimizer of E. Can you explain it again if you?
Yes, of course. So you see, we want to find some, for instance, some W such that W on the boundary of D equals to H. Okay, this is a condition that you wanted to satisfy. Plus, you want this W or U to minimize this this function, right? You want to find some W or you want to find some U such that on the boundary it is H, but it will minimize your energy. Okay, this is what you want to find. So which means you want to find this is so-called the minimizer of this functional. Okay, which means it's a minimizer of this form of a function. And we have the constraint, this star, right? And also this star. On the boundary, it equals to H. Okay? And now the idea we have is, suppose U is a minimizer. So which means this function U makes the energy to be the lowest energy. Then, if we add a little bit of any other function, such that is still on this family of functions, then it must get the energy to become a little bit bigger. Is that clear? Is that clear? Any question about it? Any question?
So we're looking for minimizes the energy, and which satisfies the boundary. And so we're taking U plus epsilon V. Why do we do that?
Because you can see this is another function satisfy the boundary condition, right? And since it's different from U, you move it a little bit, then it must become, well, the energy must become a little bit bigger for any epsilon. This is the same as where you try to find the minimizer of a function, right? When does a point be the minimizer of your function? It must look like this, right? Which is, this is a minimizer so that if you move a little bit of this point, then it can only become, this value can only become bigger. It cannot become smaller. Then in this kind of situation, it is at least a local minimum. Right?
Oh, okay.
So here we just change it to function. Okay. So that means, okay. That means you must have this E U plus epsilon V is greater or equal than E of U for any epsilon. Okay. And any V on the boundary is equals to 0. This must be true. Then let's try to expand it and see what happens. Okay, if we try to expand it, then what happens is on the left hand side is just EU, right? Right hand side is it's EU, right? Plus epsilon square EV. It's a quadratic formula. Plus, well, this inner product of these two guys, so it's inner product of well, epsilon times 2 times gradient U gradient V dx is greater or equal than E, right? We must have this. here, what we can do is we can do another change. Well, we can do another. Well, this Green's first identity, right? For this intersection term, for this well, the term both have u and v. So what we will have is epsilon squared ev plus the boundary term just disappear, right?
Oh, I'm sorry. Give me. Can I ask one more stupid question? So why is this integral on PDE is positive?
Which integral is positive? This one?
Yeah.
This one. This one, well, if you take u equals to v, then it must be positive, right? But v may not be equal to u. Maybe v may be anything. We don't know whether it's positive or not. We can only do some, well, we can only play with it, right? It could be anything. Depends on what is your u, what is your v.
Okay, so how
we
do
don't know.
how do we get an inequality then?
How do we get this one? How do we get this inequality? Because we have this first inequality on the first one.
Oh wait, so we assume it first, and
We
then
just
we
do the quadratic equation, right? We just do the quadratic formula to expand it. It's,
Wait,
well,
so-
maybe this e.
So we basically assume that u is a minimizer already, and we had
Yes.
this in the first inequality.
Yes, we assume that, and we try to see what kind of condition you must satisfy.
Okay, sure, got it.
So we can use Green's first identity again, and if you use that again by using the boundary of v, the boundary value of v equals to 0. So the only term that left is minus 2 epsilon, well, v Laplace u dx. And this EU and EU from both sides, you can cancel them out. It's greater or equal than 0. Okay? So, this means epsilon EV is greater or equal than V Laplace U dx. Now, for fixed U and V, you can take epsilon to be arbitrarily small, right? Since your V could be arbitrary, it could be non-zero for sure. So which means the right-hand side is something could tends to 0. The right-hand side must equals to 0. Right? So we must have this v plus u. You take this integral on d dx equals to 0. For any v on the boundary equals to 0. You give me one v, then we must have this inequality. Okay. Then from this step, how we can show that Laplace u equals to 0? Let me ask you a question. How we can show that Laplace u equals to 0? Any idea?
Oh, actually, I'm still stuck at the previous statement. So, how do we know it's 0? I'm really sorry. I'm asking questions every 5 minutes.
That's okay. How we do what?
How do we derive that the integral is supposed to be 0 from this previous inequality we got?
Well, you can see that first we can take, for instance, epsilon to be positive or negative, right? Here we assume that epsilon to be positive. Okay, maybe I should write it more clear. Epsilon to be positive.
Oh, and so we just take epsilon as small as we want until we just get that this. Okay.
So this integral is less or equal than 0. And moreover, it's greater or equal than 0, right? So you get what you want. Right? So my question is, suppose you have v times Laplace u, you take the integral equals to 0 for any v. How can you know that this Laplace u must be equals to 0? Any idea?
Sorry, I also have a question.
Of course.
How we can get the let me see, the third inequality.
The middle one, this one,
Yes.
right?
Yes.
Well, you can see that you have this, first you can cancel this from the second inequality, you can cancel EU both sides, okay? So you must have this epsilon squared EV plus 2 epsilon, this integral is greater or equal than 0, right?
Yes.
And by the Green's first identity, this will, this term is equals to minus this guy minus v Laplace u,
Oh, I see.
plus, right, plus the boundary term. And the boundary, on the boundary, your v equals to 0, which is why you must have this identity.
Okay, got it.
Okay? Mhm.
Thank you.
Okay. Any other question?
Sorry, it's in of weight of its number.
E is E, what E?
I like the energy. Energy.
Energy is just a number, right? Energy is just a positive or a negative number.
So like for each fixed.
Because for each fixed function, energy is just a number. It maps a function to a number. Right?
I see.
Mhm.
Thank you.
Any other question?
So we must prove that the Laplacian is equal to 0 by knowing
We
that
want to
this is
prove the
true
Laplacian.
for
Why
any
is that?
v. So can we just take like a constant v so that we can take it out of the integral? So we get that the integral is equals to 0, and then by vanishing t or anything, you get that Laplacian of u equals to 0.
Well, if you only get the integration of the Laplacian of u equals to 0, that doesn't really mean that Laplace u equals to 0, right? You may get some kind of, for instance, you may get some kind of Laplace u equals to some function, right? And this function, it may take the integral, it's equals to 0. You cannot really guarantee that this kind of situation will not exist.
Wait, I think we can try to like find a bound for the Laplacian. And so if we have a bound, then it would be easier for us to get it as equal to 0.
How you can get u is an arbitrary function, right? We only know that it's a minimizer of our energy. Then how can we get some kind of bound for u? So you have a function. Pair with another function could be somehow arbitrary. It is 0. You take the integral, it's equals to 0. Does that sound familiar to you? This is actually a problem in your homework last time, right? It's homework 4th problem. You show that for any g, you have f hat times g is always equals to 0. And you want to conclude that f equals to 0. You remember this problem? And how you can do it? If you use this, this inversion formula, right? And then you see that, okay, since this g is arbitrary, so this g could be arbitrary. Then this f times an arbitrary function equals to 0. By some techniques, you know that this f must equal to 0 if f is continuous. What kind of techniques do you use?
Like the Fourier inversion theorem and like the bounce function, right?
Yes, well, you just use a bump function, right? Well, how you can guarantee that f must equals to 0? Well, that's not so hard. For instance, if f at some point is not 0, then that means in some small domain, for instance, it's positive, then in some small domain, like from this is x0, from x0 minus delta, x0 plus delta, from this domain, you must have this fx is positive, right? It has a lower bound. Then what you can do is you can try to choose g to be some bound function on this domain, right? It's equals to 1 on this smaller domain and equals to 0 outside. Then what you can say is this integration is, well, it's at least something like 1/2 this kind of domain to delta times f0, fx0 divided by 2. Okay, which is something maybe I should go through it tomorrow again. Okay, and which is positive if you choose such kind of bound function. Okay, and which is a contradiction if you choose g hat to be this kind of bound function. You get, okay, at least on this domain, you have some positive, exactly positive integration, which is not 0, which is why you got a contradiction. Okay, so similar things here. If you want to say that Laplace u equals to 0, then what you need to do is, for instance, if at some point your Laplace u is not equals to 0, then that means on a very small ball around this point, it is still not 0 and it has a lower bound. Okay, and you choose v to be a bound function of a slightly smaller ball of this ball. Hello. You have a bound function with a slightly smaller ball. Then you use this v to multiply this Laplace u. Then this v times Laplace u only supports only non-zero on this ball, which is positive, which your u is positive.
Sorry to interrupt.
This integration.
Professor, can you hear me?
I can hear you.
Oh, can you explain what happened just now? Sorry, my connection was really bad and I didn't see anything.
Okay. Yeah, it seems that WebEx it still doesn't work well. Sorry about that. Well, but at least it will not just get end from my end, which is why I think it's a little bit better from Zoom. Okay, let me explain it again. Okay, so basically what you're trying to do here is, suppose you have one point such that the Laplacian u is not equals to 0. Okay, then we can show that since Laplace u is continuous, so we can show that around this point there must be a very small ball such that Laplace u is always greater or equal than some positive constant. For instance, Laplace u equals to something like f at x equals to x0. Okay, then we must know that Laplace u is greater or equal than half m around this ball, well, around this x0. Okay, then we can choose v to be a bump function, and really good bump function, such that this bump function is only 1 on this on this ball and 0 on this. So you will multiply this v by Laplace u, will give you something more or less like, well, on this ball, your Laplace u is equals to Laplace u. Otherwise, Laplace u is just a 0. And also v is smooth. Well, that's a good question. We always assume the function we discussed at this moment are very good function, are smooth. Okay, so u are smooth. U is smooth. Otherwise, it will be hard problem. We try to do it well, not so rigorous. Okay. So then, as long as you assume that u is twice differentiable, and you will get this kind of plot. You don't have any point such that Laplace u is positive or is negative. Okay. Yeah, maybe you're right, Chen. Maybe we should say that, okay, for those and omega and w is at least a C2. Okay, otherwise it doesn't really make sense. So we will assume in today's lecture and tomorrow's lecture, we will assume everything is just as smooth. Okay. So we get it. This is a very important idea in analysis, which is like a cutoff. Use a bump function to do a cutoff. Okay. Any question about this? Any question? As we mentioned, we're going to discuss two identities named after Greene. And well, we are going to discuss about the Greene's second identity. But before that, let's have a short break. And well, let's resume at 5 o'clock. Okay. Sorry about this network issue. Hopefully, next time I will try to find some other place. Maybe it will work better. I hope. Yeah, I also see that. Well, no, well, this is something different. This is from my program, and I am recording. It's a different thing. I think it's a different thing. Don't worry about that. Maybe I can. Yeah, this. Well, then you don't see 0, 0. Okay. Yeah. It's for some stupid issue. Yeah. hopefully this Okay, we should go back. Can you still hear me? Hello, hello. Can you still hear me? Great. So now let's study what is Green's second identity. Okay, Green's first identity is nothing but just an integration by power. You can see that. Basically, it's just the integration by power, nothing more. Then, well, when you try to study this Green's first identity, you will find it's a little bit weird because U and V from this identity, they are in different situations. So, which means this identity is not symmetric. Okay. So what if we replace U, we just swap U and V on this identity? Then we got another identity, right? But that doesn't change. But then what if we do a subtraction of these two identities? And what happens is this term will be cancelled. If you swap U and V and take subtraction, what you will get is you still get this term, and well, this term will becomes U partial V minus V partial U, right? And on the right hand side, it will be, because this term, the middle term, just disappear. It will be V, well, U Laplace V minus V Laplace U. Okay, this is so-called the Green's second identity. It is super easy. Getting from, you can easily get it from this Green's first identity. Okay. Any question? So you can see that this is actually some kind of a boundary condition directly with connection with Laplace, right? So it's very, well, it's very straightforward from the boundary condition to Laplace. And just to write a quick remark here, that is, on the right-hand side, it is some boundary condition. You can see that if U and V are both some functions satisfy the homogeneous Dirichlet boundary condition, or homogeneous Neumann boundary condition, or the homogeneous Robin boundary condition, then the right-hand side are both equals to 0. Right? If U equals to V, both 0, or partial U partial N, partial U partial V partial N equals to 0, or partial U partial N plus something, something times V, something times U on the boundary is equals to partial V partial N plus something plus times V on the boundary is equals to 0. Right hand side, left hand side of G2 are 0. Whatever condition you have. So for this kind of boundary condition, homogeneous Riemann boundary condition, homogeneous Dirichlet boundary condition, homogeneous Robin boundary condition, we call them symmetric boundary condition. Just the name. Okay. And for this kind of boundary condition, it might be easier for us to deal with, because on one side it is 0. And this will Green's second identity seems to be even more complicated.
Question before you go on.
Of course.
So basically, So the condition that's called symmetric boundary condition is that this left-hand side should be equal to 0, or is that the integrand of
Yes.
the integral should be equal to 0?
Well, as long as u and v both satisfy this boundary condition such that it makes the right-hand side equals to 0, then it is a symmetric boundary condition.
Okay.
Basically, it's well, an integrand also equals to 0. It's well, it's normally what we have. It's just a name. Okay. Normally, if we say the symmetric boundary condition, we just mean these three kind of boundary conditions. Okay. So let's see why this Greene second identity is also very important. It seems well, it's just some kind of complicated formula, right? Why it's so important? Let's see the first example, which is so-called representation formula. Okay, so the representation formula for the harmonic function. If u is a harmonic function in D, okay, let's say D is in R3, so it's a 3D problem. Then u at any point, it can be written as the boundary value minus ux partial n 1 over x minus x0 and plus 1 over x minus x0 partial nu ds divided by 4 pi. Okay, so you can see that for a harmonic function, if you want to find the value of it, you just need to know the boundary value of it. Then you are able to recover it by this formula. And this are just some particular functions, right? Nothing more than that. Before we move on, any question?
Wait, I am confused. Where this this equation come from?
Where does this equation come from? This is something we are going to prove. It's not so easy to prove.
Okay.
Okay, it's not so easy to prove. This is a very interesting formula, and it's a very important formula in analysis. Well, this is really confused because, yeah, this is really confused. I agree with you because it somehow looks like, at least the right-hand side looks like the left-hand side of your Greene second formula, the Greene second identity, right? But the left-hand side, ux0, it doesn't look like something like this integration, right? It's something different. It should be something different. So how you can write this ux0 to be something on the right-hand side of the Greene second identity? This will be a problem, okay? But of course, you can see that, well, if you want to prove this, then we must take from the G2, you must take V equals to 1 over 4 pi x minus x0 with minus sign. So that it will look like at least the right-hand side of G2, right? Now the only problem is how you can show that if you take this particular V, the right-hand side is, well, the right-hand side of G2 is actually equals to ux0, right? Well, intuitively, you can see that on the right-hand side, what do you have? u is a Laplace, well, it's a harmonic function, so this term disappears. So basically, what you get is u times Laplace v, u times Laplace v. After you take the integration, it goes back to ux0. Okay, so in the future, if you learn something like functional analysis or some course in ECE, you know that such kind of function does not exist, but it can be somehow give it intuition of this kind of function. What does this kind of function looks like? It's so-called the Dirac delta function. Okay, and this u times Laplace v, this Laplace v is equals to this Dirac delta function evaluated at x minus x0. Okay. But of course, you don't know what this means. And this Dirac function is just some functions such that when this x equals to x0, it's infinity. Otherwise, it's 0. I know that there is no regular function such that it looks like this, right? But this is why we call it a generalized function. It's actually not really a function. It's equals to infinity when this equals to 0, or when x equals to x0, and equals to 0 elsewhere. And if you have this kind of function, multiply u and take the integration, you will get back to ux0. Okay, but we haven't learned this before. You haven't learned what is a functional analysis. You don't know what is a generalized function. So let me prove it for you. Okay, why u times Laplace v is equals to u at x0. Okay, let's consider our domain. Looks like this. Okay, let's say this is our domain D, and for instance, your x0 is somewhere here. It's somewhere here. Okay, and that's trying to do a cutoff at this point. Let's say we take a cutoff of radius r of this x0. Okay, and well, without loss of generality, for simplicity, we assume that x0 equals to the origin. Okay, just a 0 for simplicity. Then v is actually equal to minus 1 over 4 pi r, and r is the normal x. Okay, and then we take another domain instead of D. Let's take let's say this S0 is the origin, and let's take this part of the domain, and that's try to take off a disk or a ball around this origin, around this x0, such that, well, you don't have any singularity of this v. Okay, d epsilon is d subtract a ball of radius epsilon at the origin, centered at the origin. Okay, this is your new domain. Is that clear? So this is your new domain, the shadow part. Then, well, we know Laplace u equals to Laplace v in this disk. Well, in this domain, in this new domain. Because your v is nothing but a regular function at this moment. And, well, I think last week we have already shown that this kind of function is indeed Laplace. Well, it's a harmonic function whenever your r is not equals to 0. You remember this? Because it doesn't depend on theta, so well, you can try to in dimension 2, you know what is Laplace 2. In dimension 3, Laplace 3 is equals to, you take second derivative in R plus R, well, 2 over R, partial R, plus 1 over R squared sine theta, partial theta sine theta, partial theta, and plus 1 over R squared sine theta squared, and partial phi squared. Okay, you can do the calculation yourself, and you will find that this v is a harmonic function everywhere but at the origin. Okay. Any question? Then let's use the Greene second identity to our new domain d epsilon. Let's see what we get. Okay. So Laplace v and Laplace u are both equal to 0 on this new domain d epsilon. But the right-hand side is not, right? The right-hand side, what you should get is on this partial, well, what is the boundary of your new domain? The boundary of your new domain consists of two parts. One is this old domain's boundary, this boundary of D. Another domain is this part, right? Because you take it off. So the domain should be the sphere around this origin, right? It's a sphere. So it consists of two parts. So which means you must have this partial epsilon, this partial d epsilon, u partial n v minus v partial n u ds equals to 0 by the Greene second formula, Greene second identity. These two guys, Laplace u and Laplace v, are both equals to 0. Okay. Okay, that looks pretty good because we know what does it looks like, right? It looks like partial d u partial n v minus v partial n u. This is the right-hand side of your representation formula. And it must equals to minus of partial b epsilon 0. Okay, on the sphere of radius epsilon. And u partial n v minus v partial n. Is that clear? So we have this. Okay. We don't do anything. We just split our boundary of d epsilon to be two parts. Okay. Any question?
Sorry, could you please explain why it's equals to Laplace v equals to 0?
Well, because first, Laplace u equals to 0, right? Because u is well, harmonic function, right?
Yeah.
And why Laplace v equals to 0 is simply because on 3D, if you try to change the coordinate to something like the polar coordinate, but we call it the spherical coordinate, then you can write the Laplacian in this form. Okay, it's partial r square plus 2 over r partial r, okay, plus something you take derivative in theta and phi. This is something you have to do the algebra, okay? And then you can see that, okay, if you plug in v, you got 0.
Okay, I will try that later.
Yeah,
Thanks.
yeah. So this is a kind of this is kind of a function. V is a function such that it only depends on the radius of your variable, which means it doesn't depend on the angle. Thus, it is a Laplace function. If you want to find the function both satisfy these two properties, then you find that you can solve an ODE and you find that, okay, this V must be of this form up to some constant. Similarly, in 2D, you may get a different V. Okay, in 2D, well, your Laplace 2 is equals to what? Is equals to some partial theta square. I forgot, maybe there should be a 1 over r square plus partial r, partial r. This is your Laplace on 2D, right? So if you want to get something similar to, well, the same thing 3D, what you really want is you want to get V in 2D to be log R. Okay, so we will have the similar representation formula in 2D by replace this 1 over x minus x0 to some constant times will log R. Okay, log x minus x0.
Sorry, Professor.
Mm-hmm.
Don't do we need to mention the direction of the boundary, because I think by apply the divergence theorem, what we get is that the direction of the boundary is like counterclockwise. So uh,
Well, don't
uh,
think it that way, okay? We don't try to or find the oriented of this boundary, okay? We don't want to find the direction, well, the origin of the boundary, because
like
always use this kind of notation. Hmm?
I mean, from the equation that the integration over the boundary of the epsilon is 0. We can get the following formula, but there is a minus sign, so I think there is need to mention the direction.
Well, the thing is, when you take this surface, well, this surface integral, you don't really need to determine the oriented of this surface. Okay, it's just like when you have a circle or when you have a curve, you try to take this well the integral along this curve, then well we already assign this oriented of this curve to be already assigned. Okay, so
Sorry,
you don't need to worry about. Hmm?
sorry, I understand it. My
Yeah, okay, but you are right. Well, this is a 2D case. You are right in one thing, that is, then we have to be careful about this partial n, because if you take this kind of well sphere to be your boundary, then the n direction, which is the normal direction, will point outward of your domain, must be on this direction. Okay, because you can see that you must point forward to your point, that is this kind of direction, not the other side. Okay, so which also means partial n is actually equals to minus partial r. Okay, you only want to check along this direction, how does your v change? Which means you want to check what is the change of v along with this well r direction. Okay, so if you can understand this, then we can get a very easy, well, estimate. Say that, okay, it's actually minus, but you have a minus, additional minus sign here, so it's actually plus partial b epsilon 0. Here it becomes u partial n. Your v is minus 1 over 4 pi r minus 1 over 4 pi r partial, well, this is r, u ds. Okay, you don't have this minus sign, and you change this partial n to be partial r. Okay, but you can see that this is something doable. This is something computable, easily computable, right? This one is actually 1 over 4 pi r squared, right? And this is 1 over 4 pi r. Over 4 pi r squared. That's great, because we know that your point, all the points along this on this integrand are on the sphere, right? So your r is always equals to epsilon. So we always have the, well, this is equals to, we take the integral on this, well, sphere, u times 1 over 4 pi epsilon squared plus, well, you take this integral 1 over 4 pi epsilon, because your r is always epsilon, right? We must have this. Is that clear? Is that clear for this part? Any question? And if you agree with this, first term, you get the mean value plot is equals to u0, right? Second term is something, right? It's something we don't really know, but you can find that, okay, partial r u. We assume that u is smooth. Okay, we assume that u is smooth, so it's bounded about by some constant. So the second term is bounded about by, well, some constant times the area of your sphere, which equals to 4 pi epsilon squared. Right? And if you divide by 4 pi epsilon, you divide by 4 pi epsilon, then what you get is m, a constant, times epsilon, which tends to 0. As epsilon goes to 0. So what you get is, well, this right hand side is equals to u0. And we know that u0 is actually ux0. Assume x0 is just a 0. Okay, we can move it back and then it becomes 0. It becomes ux0. So that's the end of our proof. Any question about it? Any question?
Sorry, could you explain the meaning of partial U divided by partial R?
Well, why is what? Why is this one?
No, like just the meaning of partial U divided by partial R.
Oh, partial u over partial r. You mean this one, right?
Yeah.
Partial
Yeah,
u.
just the,
Yes. Yeah. U is a function of x, y, z, right? But we can also change it to the spherical coordinate, which can be written as r theta phi. Okay. Then what is partial u partial r is just you take derivative in terms of r for this function.
okay. Thank you.
Okay. Mm-hmm.
Thanks.
Any other question? One additional remark is in 2D, two-dimensional, you have the similar thing written in this way. Okay. Now it's a line integral instead of a surface integral, and it's ux partial n log x minus x0 minus partial u partial n log x minus x0 ds. Okay. It seems that we cannot finish it today, but I will leave this, I'll leave this question to you, and maybe next time we will discuss it and try to finish it, because this part I think maybe it's more useful for you in trying to solve some engineer problem. No, this will not be on the exam. At least, well, until this point, it will not. The rest of this, this session's course will not be on the exam. Okay. If there will be something on the exam for today's lecture, it will only be about the Green's first identity and the Green's second identity. Okay, no more than that. Well, the question I would like you to think about is, you can see that u is equals to u on the boundary partial, well, something over, this is, well, 1 over x minus x0, right? And, and then it's partial n u 1 over x minus x0 and ds over 4 pi. This is a representation formula, right? But if you really want to solve a, well, problem, Laplace equation with boundary condition, then you probably only have like one boundary condition. Something like this, right? However, in this representation formula, it asks you to have both minus u and partial nu. So it seems that from this representation formula, it is not enough for you to solve the Laplace equation. This is really weird, right? Otherwise, maybe you may guess that, what if I gave you two boundary conditions? Of course, then you can see that, okay, u must be equals to this thing, right? But as we mentioned, this two boundary condition might be too much, which means you may not have the consistency of your system. Okay, your solution u might be overfitted. So this is actually a contradiction, which is, if you have this kind of representation, then how can you really solve a real problem and trying to find the connection between on the boundary, Dirichlet boundary condition and Neumann boundary condition? In order to solve this, you need so-called the Green's function, which I'm going to discuss a little bit on tomorrow's lecture. Okay, so that's all for today, and well, I will still be here until 6 o'clock. So yeah, otherwise, if you do not have any questions, feel free to go, and we'll meet again tomorrow. I'll try to figure out maybe some other way to get rid of this kind of issue. Hopefully, well, I cannot guarantee. It seems that I have no way to try. But anyway, yeah. So let me stop the recording.